right, well, I think we're going to go ahead and get started. Thank you so much for attending our session today. My name is Amanda Houston, and I'm the Chief Customer Officer for Pondera Solutions. If you've attended our sessions at past NAMPI conferences, you know that we like to try to bring topics that are a little bit different, perhaps challenge things, make you, give you new ways of thinking about things you may already do or things you never even thought you should be doing. You may have seen some of our past sessions. We've had convicted felons here. We've had doctors here. We had a great session a couple years ago in Miami. Some folks came by the booth this morning asking me if we could bring those detectives from Miami back. I'm going to work on it. I got to see what kind of new frauds they've found lately. But we really enjoy providing, hopefully, meaningful content to everyone. So do appreciate you guys taking the time to be in our session today. So the background on what we're going to talk about. And then we'll introduce our panelists. Essentially, AI is a word that I really, in my prior experience as a program integrity investigator and a lieutenant and a director, had really not heard very much up until recent years. And I thought I had this idea of what AI was. Of course, in my extensive technical experience and data science background, I knew what AI was. And then I came to work at Pondera and started actually working around data scientists and really understanding what artificial intelligence and what machine learning really are. And then I quickly realized that, job security, we're going to be fine. Us human beings that do the PI work are going to be just fine. And the reason is that there's really this amazing magic that can happen when we leverage these technologies and we partner them with people. By themselves, they are never going to be an easy button that is going to find fraud. One of the biggest challenges I have as a chief customer officer at Pondera is after we, are awarded a deal or, we sign a new contract with a new account, I come in and immediately am faced with this customer expectation of, well, aren't we just going to push an easy button and the computer's going to find all the fraud for us? Can't you just, mash that sucker down? That was easy. And it just isn't that way. And the wealth of experience that not only our team has, but your team has specific to your state or your program is essential to getting it right. And so it really is a partnership where we can leverage the machine as one partner in the process. And so that was the sort of the nexus for bringing this session to the table is level setting what is artificial intelligence and machine learning, what does it mean for healthcare fraud, and then how can we leverage it to truly be a powerful tool, a force multiplier for us, and really that there isn't that easy button. And if I find the easy button, I will definitely let you know, but I'm pretty confident not anytime too soon. All right, so we're going to talk about the concepts generally. We're going to talk about how they're used in healthcare data analytics. We're going to present some case studies. It's my feeling that every presentation should have a few war stories in it to make it exciting. So we've got a few of those in there. And then I thought it would be really interesting to bring in some things that you can take home. I'm a really big fan of giving you a takeaway. One thing that you don't need to find a vendor to do for you, a little something you can do on your own, bring back to your team in every session that we do. So we're going to provide you guys with a little bit of that. Okay, so let me introduce the rest of the panelists that have offered their time and talents to us today. So first here on my right is Jean D'Angelo, and we're very fortunate to have Jean with us on our Pondera team as Director of Analytics Innovation. And Jean is, when you say like one of the pioneers, he really is one of the pioneers. He's going to share some pretty cool stories back in the day in Florida 25 years ago and what they were doing with data science and finding healthcare fraud. Next, we have Jacob Gray, who is currently the studies manager at General Dynamics. I've decided, Dan, I think he needs a different title because it doesn't really speak to what all Jacob is and does for GDIT. So, and then lastly, we have Carrie Geiger, who is an Azure data and AI specialist with Microsoft. Pondera and Microsoft work incredibly close together, both on the data science side, but also utilizing Azure for Government as a hosting environment for our solution. In Azure Commercial. So we're very, very fortunate that Carrie has offered her time to be here today. Okay, so the first thing we're going to do is we're going to talk about, well, what is AI and machine learning? So, Carrie?
Sure. So often we think of AI and ML as competitors to human intelligence, right? People are afraid of them. They think their jobs are going to go away. It's just not true, as Amanda said. Actually, when you apply AI, you infuse it into your solution, to your business, to whatever it is that you're working on. What you find very quickly is that you get smarter, you get faster, your insights get clearer. And really what we end up with is a faster time to market for solutions. Oh, I should have looked at the slides. I'm not going to read you this, okay, because this is the definition that I pulled so that you have a book definition of AI and ML. In reality, the point behind this is here's what AI is. It's machine learning and human intelligence have been put together to build algorithms, but that doesn't matter to most of you in the room. The reality is what it means to you is faster, stronger, better, quicker, right? More agile, more advanced, and it's repeatable. That's the really exciting thing about where we've taken AI today. So really what we end up with is an engine in AI. Think of AI specific, so just to put the two together, AI and ML really they're not interchangeable, but they also don't exist entirely without the other. The real power comes with leveraging AI from machine learning and then having a human create the boundaries, which is what these guys can talk to you about how to make that technology work. Because like Amanda said, you can't just program it and expect it to work long term. Yes, it is repeatable, and yes, it will keep going, but it doesn't tend to get smarter if you don't interact with it and basically give feedback to tell it how it's doing. So the reality of AI and ML together is they create an engine that facilitates human capabilities on a level that they weren't available before. Artificial intelligence makes us faster time to market, as I mentioned, but more than that, it really takes to the next level the things that one person can do. You extrapolate that into what a team can do, and all of a sudden you can solve problems that were completely out of reach prior to combining people and technology. So there's a little bit of history of how we got to where we are today. AI, sort of as a concept, came up around 1950 or so. There was a lot of constraints, depending on how much you know about computers back in the 50s. They were expensive, they were ginormous, they were very, very slow compared to what we know of today. And the idea of having tons of data storage, which is what you need to do ML and AI, any kind of data science, you just didn't. It was not achievable for most companies. So we made some improvements, but really it took a while. And by 1980, we ended up with the first solution. This is not Microsoft, like the broader space of data science and technology came up with an expert solution. Think of that as something that can produce the same results as a human expert. Then things really started to take off. I suspect anybody who's anywhere close to my age or older knows about the famous chess game. In 1997, IBM's Deep Blue went up against the world chess champion, Garry Kasparov, and you know who won, right? Computer. And also in 1997, Microsoft started using AI within our own products. So you notice, if you recall, when we started to filter out junk mail, that's AI. Figuring out, based upon a pattern and a history, what you are or aren't going to care about. Now today, really, we are in very much a big data world. We've been in that big data world for some time. Space, you can have as much as you want to store. Data's cheap. You can spin things up in the cloud in Azure. You can have as much compute as you need to. So now we're right back to where we started with needing the human intervention, because what we have to do now, technology is not your limit. There's no bottleneck. Microsoft will sell you as much Azure space as you want. Take it from me, that's what we do. But that's not going to help you until you have somebody that can help you build the science, and not the science in terms of the code, build the intelligence around what it is you're after. And really, the sky's the limit for what we're going to be able to do.
Great. So we're going to talk a little bit about how we can use the technology capabilities and the data science behind them in healthcare data analytics. So, Gene?
Okay. I'm going to start with a little machine learning trivia. It's actually going back to 1994, and in a place not too far, just a short drive from here in Jacksonville, Florida. I think I've identified possibly the first ever successful application of machine learning in healthcare fraud detection. There was a PhD student at the University of Central Florida, and he was looking for ways to apply artificial intelligence. He happened upon the Medicare fraud branch in Blue Cross Blue Shield of Florida. And at the same time, there was this new database system called HOPS, or Heuristic Optimized Processing System, which was probably the first database system designed specifically for analyzing big data. So this very brilliant practitioner designed a custom machine learning model that actually took all the claims, say for a year or 2 years, and concentrated them down to the most tightly knit network in the entire database, and just one network, the absolute tightest network, and actually maximized the links to entity ratio. In doing so, he found a very large fraud ring in Southeast Florida. No surprise, Southeast Florida, right? It was over 150 providers. They had built over $200 million in 18 months from the Medicare Trust Fund. And there were almost all of these services were non-rendered. So it was a very blatant fraud. It became an extremely large FBI referral. At the time, so this was a great start. This is kind of how it all started. But unfortunately, there weren't a lot of financial incentives at that time to keep the ball rolling. For one thing, the Medicare fraud branch was actually part of Blue Cross Blue Shield of Florida at the time. Well, guess what they did? They processed claims. And the more fraud that was found, the lower the claims volume went down, decreased. And as a result, they lost money. So they were not too happy about that. So it didn't go over too well. So fast forward to today, and we have now in the area of classifying healthcare providers, it's fraud and non-fraud. We have basically two approaches. One is supervised machine learning, and one is unsupervised machine learning. So supervised is where you take a population of providers that have already been identified as a fraud and non-fraud. And then you use those and with machine learning algorithm to find out how can you separate in other populations the fraud from the non-fraud. And so it's a good concept. There's some problems though with supervised learning for healthcare fraud. One is that there is a high degree of what they call class imbalance in these training sets. Usually the number of fraud cases is about 1% of the number of non-fraud cases. And machine learning algorithms work very well in that case, but they come out with saying, well, just classify everybody as non-fraud and you're going to get a very high performance rate, like 99%. So that doesn't work. So you have to somehow remedy that problem. And one of the techniques that's been used in academia most recently is something called random undersampling, where they undersample the non-fraud class in order to bring it more in balance with the fraud class, the fraud class. So 50-50 or maybe 35-65 or something like that as far as the ratio goes. The only problem is that has been done, but as it turns out, it doesn't work all that well in this particular area. And in fact, it often comes out to be something of a profiling tool. To give you a rough example, for example, if you did a random undersample of the general population and you were trying to find people that were guilty of money laundering, well, guess what? You'll come out with a very simple rule. If they're rich, they're money launderers. Well, unfortunately, you can't say that everybody that's rich is suspicious of being a money launderer. Same thing here, what they came out with, well, if they're a particular specialty, you're probably fraudulent. Well, we know there are certain specialties that are more likely guilty of fraud than others, but you cannot use that and go out and audit everybody that's in a particular specialty. So it's sort of a useless conclusion, and it is kind of a type of profiling. The other problem, so I was going to say the high performance measures, I call them when you get, and in the academia they did get like 80% performance rate by using this kind of study, but it was fool's gold. You know what that is? It's fool's gold. It looks shiny, but it really, when you get down and interpret it, is not so much. Now, the other problem with the training set is the high error rate in non-fraud cases, because we only find 10 or 20% of the fraud that's out there. I mean, maybe you didn't know that, but there's a lot that we haven't found. And as a result, in the non-fraud case, there's a lot of errors because there are really fraudulent providers in the non-fraud class. And so that produces a high error rate, which also creates a problem for the machine learning algorithms. And finally, fraud is not a monolithic concept. There's many, many types of fraud. And based on the way the machine learning algorithms work, unless we find some kind of a magic characteristic that separates good from evil, you're going to need many different different machine learning algorithms for each type of fraud. The other kind of machine learning is unsupervised. Unsupervised, you don't need a training set. You don't need to have that type of a background, so you don't have the problems the training set brings with it. And what you do is you group providers together based on their similarities of one type or another. Two ways that we use it is for network analysis and cluster analysis. So for network analysis, we group providers together based on their similar connections, either to themselves or to others. And one of the most popular ways you're probably aware of doing that is using shared beneficiary analysis. So that's one way of doing a network analysis. Cluster analysis is we group providers together based on their similar practices. So looking at how they utilize diagnosis codes, procedure codes, and so on, we find providers that have similar behavior patterns in that regard. Now, since we're looking for aberrant situations in these cases, you don't know how many clusters you're going to have from when you start out. And as a result, you have to use something called hierarchical clustering to find the aberrances. And so you'll find probably a lot of large clusters and a lot of small clusters that are aberrant. And that, unfortunately, a very computationally demanding type of problem to solve. But it has been solved. We've been doing it, and it produces very interesting results. And then finally, the clusters are very good at finding new and unknown types of fraud, because you're not basing it on something fraud that's already occurred. So you might find an aberrant cluster that has fraud that you never knew existed before. But the problem is you have to go through a lot of innocent aberrances to find that. Now, there's often some low-hanging fruit. So if you do review a couple of hundred small aberrant clusters, you might find at least one or two that you definitely want to follow up on. So we've been doing something called the hybrid approach. And basically what it means, and you go ahead and just knock all 6 of them down. What it means is to first apply the unsupervised method to identify the clusters and networks, and then take a training set, which doesn't have to be as good as it would need to be for supervised learning, and label the providers in those clusters and networks. And then based on that, if you have clusters and networks that have an unusually large number of those labeled providers, you probably want to look at the other providers in the same cluster and network. So it's a fairly simple concept, but at the same time, it's not all that simple to implement, because if you've got cases, and we would look for case histories, and your own case histories as being the best place for these, because you're dealing with your own providers. You're talking about cases that have been prosecuted. Well, they're not doing the same thing now they used to do. So what you have to do is go back, and we've gone back to like 2015, and do a complete cluster network analysis, apply the labeling concept, identify all the providers that are in those clusters and networks, and then follow them to the current day and see what clusters and networks they're a part of. And you learn a lot from the way the providers morph and the clusters shift and reorganize and so on. But that is what we call the hybrid approach to using supervised and unsupervised learning.
Jean, can we just pause right here too? I just want to interject for some folks in the room, like a real world application of what Jean's talking about that we're using and we're seeing some success with. So how many of you have had a successful investigation involving a provider who completely committed their fraud on an island and wasn't involved or connected in any other way to any other provider in the program? Doesn't happen that often, right? It's pretty rare. So one of the ways that we've found that this has been so successful for us is you can literally find all the tentacles of the octopus, right? So it's a way for us to take one good find and turn it into 8. It's a way for us to actually make a big enough dent that we know the mole is going to pop out of another hole soon enough, but if we can delay it for a little bit longer, and save some money in the process, this has been a really, really successful approach for us in terms of just expanding on a particular successful lead and finding 8 or 10 other connected providers related to that entity. So I just wanted to kind of bring that back to, more of a real world application that is working for us at Pondera. Go ahead, Gene.
Okay. Next slide. Okay, actually, I'm going to now turn this over to Jacob, and he's going to expand on these concepts.
Hey everyone, some of you have heard me speak several times, so if you're tired of it, I apologize. One of the things I wanted to bring to bear for this conversation was something we encounter a lot, which is a CAPTCHA test. Does anybody know what CAPTCHA stands for? Nobody? I thought there'd be some nerd in the room. It's a
They're right here.
Oh yeah, well there's more out there for sure. Completely automated public Turing test to tell computers and humans apart. So do you know what a Turing test is? Anybody know Alan Turing? He's a math. Joe does. I knew you would down there. I planted him down at the end. So he was a mathematician in the early 20th century, and he proposed this idea. Now keep in mind, the technology didn't exist at the time, but a Turing test was a test that one day, when a computer could pass this test, that their answers would be indistinguishable from a human's answers given a questioner who didn't know which was the human and which was the computer. So in other words, somebody asking the question of two unknown answerers, on the day they were unable to distinguish the human versus the computer, that would mean the computer had passed the Turing test. And so this is kind of an example of something I just pulled off. I forget what I was registering for, but I pulled off the internet the same day that I was thinking about this. And you guys see this all the time. This one is asking you to select a storefront. So, look at the features of these images. Like you see walls, you see roofs, you see signs, and some of them you see people or like activities going on. So you as a human can ingest all of these data points and you just know. Like we call it intuition, but it's really your human neural network, as somebody was talking about in their presentation the other day. This your human neural network bringing together this ability to identify patterns. And so the reason we still use these CAPTCHAs when you're registering for stuff to make sure you're not a bot is we're not there yet for this generalized AI ability. Computers are still not as good as you sitting there at distinguishing what is a storefront and what is not. So we're still able to exploit the distance between where we are now with generalized AI and where you are as a human with your biological neural network. We're able to exploit that to differentiate between a human and a computer. And so, the fact that a computer can't solve this relatively complex pattern recognition is just evidence that the robots versus humans, which I think is the title of this, is still a thing. We have to work in conjunction. So taking this back to the example you all work with on your day-to-day basis, if you're a data person like I am, you are trying to extract rules and rubrics and heuristics and sometimes even create machine learning algorithms from your SMEs. Those are your clinicians, your investigators. Sometimes it's a member hotline complaint, somebody that observes something in the field you can't tell from the claims data, and then you're trying to distinguish that as a pattern in the data that you do have, claims data, EMR. And so as EMR increases, and I know we'll talk more about this, these types of techniques are going to become more and more important, because if you have a SME, imagine you have a SME that can just do the sniff test on a claim or series of claims and tell you whether it's right or not. But that's one person. Maybe you're lucky enough to have 2 or 3 in your shop. So how do you scale that? If you could teach the computer or create machine learning algorithms or AI frameworks that could do that for you over and over across a vast volume of data, billions of claim lines some of us have access to, not to mention unstructured data like EMR. That's what we're talking about, is humans and computers working in conjunction to exploit the abilities of the computers using the intelligence of our SMEs in the fraud space.
Thank you. So the CAPTCHA example, I think, is really perfect transition into a couple of case studies that we're going to talk about. So the same, I kind of apply the CAPTCHA images there as a simple way of thinking about the outputs of the models that our data science team is constructing or running. And they present those to our SMEs and our work group that we've formed, which is comprised of folks with all different types of backgrounds and experience within program integrity, everything from clinicians to former FBI agents, those types of folks, because we have that capability to look at that and go, yeah, this one's the fraud and these three aren't. And then that information and that intelligence is infused back to the data science members of our work group, who then go back and tinker and make adjustments to the model output such that our system can then push those two that the team said, yeah, these are fraud and these three aren't, so that going forward, the model produces more of those two kind of providers we've identified as, yeah, I know from my experience, those are examples of fraud, where these are just high billers with a clear explanation for that pattern of claims behavior. And I think that's a really good segue into what we're going to talk about here, which is a specific example where we did just that, where we had, a model that was architected. It was, kind of batted around by our SME team, and there's like gentle arguing that occurs internally as we're kind of working through this. But ultimately, what comes out of the oven when, the pie is done baking is a really solid approach, because there's all these different viewpoints, experiences that we have, that we're looking at that data and really attaching meaning to the images that are coming out, rather than just, pushing what the machine tells us to, right? So, Gene, you want to talk about the cluster analysis approach?
Yes, and first I wanted to just mention something I did mention before, that, which is the first bullet on this slide, is that for any kind of work like this, data preparation is extremely important. And I've seen a lot of cases where they just don't put enough effort into that area. And you do data transformations, you need to do data reductions, you find ways of making the data more relevant to the concepts that you're looking for. One of the things that we use here is that for clusters, you cannot take a provider that only has 3 or 4 claims in the database and say that defines a profile. So you've got to have some kind of a minimum number of claims or dollar amount before you bring a provider into the cluster analysis. And you want to look at for the bigger ones anyway. But in this case, what we did was we did a cluster analysis, and in this particular area, it was really clear that it came up with one large cluster, which was like this, the typical guy or typical types of provider that do this type of work. And then we had 6 or 7 smaller clusters, which were atypical and aberrant. Then from there, we in one of those aberrant clusters, we found that there was several of the suspicious providers that we had identified as those we weren't going to label, so it definitely qualified as having a higher percent of those labeled providers. And in fact, the largest provider by far in the cluster was one of those suspicious providers. Then the next step, we used what we call our paired providers report. And it's actually a report listing all of the links that we use in our network analysis, which is basically a measure of the similarity between the patient mixes, the patient base of each provider, and how similar they are. We looked up some of the providers and looked up the providers in this cluster to see how they're related to each other. And there were a lot that had patient sharing involved. And so this cluster was not only a cluster, it was also a network. And even with this, much as 42% with that largest provider. And I think Amanda's going to do a play-by-play of exactly where we went from there.
So this is an example. Again, as Gene mentioned, we've de-identified it and blurred it out, but this is an exact approach where we had an output, from the cluster approach, and it was handed over to the work group, to the SME team, and we went to work, right? So first thing we noticed is that we had 3 distinct billing NPIs, a physician, a group, and a lab. And then we had a focus on 2018 paid claim amounts, and they ranged from about 250,000 to over 2 million between those 3. Using the cluster model, we identified other providers in very close proximity to this network. One was less than a block from the current provider. So to bring this home, if you are a physician, would you open 2 separate and distinct offices 1 block from each other and practice at both of them, doing the exact same services? what kind of sense does this make, right? So once again, the SMEs are looking at the CAPTCHA and we're like, nope, something's not right here. So we kept digging. The suspect, one of the suspect NPIs, administrator, was the authorized official of another entity who was already under investigation by this client's PI group. Getting warmer. The heavy similarity of beneficiaries is interesting too. So we expect to see some level of patient sharing, especially with related type services, referral networks, things like that. But what Jean's talking about with the paired provider and that high similarity index is those situations that don't make sense, where you're literally herding people between one provider and another, just kind of almost sort of shifting the list of patients. And Bob, this month you got them, and John, next month you got them. And that was some of the patterns that we were starting to see. As we started to dig into that network, Jean mentioned that surfaced. We started seeing, oh, look, these guys have been seen before. It's not their first rodeo. And we saw just a hodgepodge of former prior program integrity actions, things like, warning notices for improper billing, demands, civil money penalties, almost every type of administrative thing that can happen to you before an actual licensure action is taken. Several connected providers had been referred to state medical board in the past. It appeared that, those interventions had perhaps not worked. We did see that mostly the same program code was being used for services. We had a lot of non-enrolled providers rendering the services, and then a high percent of services were related to relatives. One thing that we noticed right away in the network is the presence of relative providers. And the head nods are because you guys know that's fairly common, but the ability to identify that even without common last names and things like that. It was broader than relatives. There was a sort of a cultural group that was involved, very tight-knit community, and perhaps where some of these relationships were formed. We kept going. So then we dug back into the cluster again and started looking at the data, and then we noticed this excessive amount of services for their patient group. So once again, once you've got your group and you're passing them around, now all of a sudden they have a lot of services, and to an extent that does not make sense. In one particular instance, we had a recipient who had 87 services in 10 months, and this is general type services. This is not specialty. This is not oncology. It's not a sick patient. We had all kinds of unexplained billing spikes. Again, could be the passing of the information from one provider to the other. And then we saw this really interesting patient ID number behavior. So as we started to kind of follow what was happening at the recipient level, we noticed that the provider was billing for one recipient, same person, with each of their known IDs on the same day for the same services. And of course, as you know, that would get kicked out of the systems. They have two separate and distinct, personas. We saw them alternating between the different IDs. So you would think if someone, came through and got another ID and a new ID, and they'd be using that number going forward. But we saw a lot of this back and forth between the multiple IDs. And of course, the new IDs all happen to be issued by that provider. Some of you are probably thinking, I know what kind of services and what program this might be in. FQHC. Many recipients never had a single claim from any other provider in Medicaid, just here. Small, tight-knit community, right? And just never needed another service. And then, our analysts, our super sleuths couldn't help themselves, and they kept digging into some open source data and started finding things like advertisement for free services, recruiting patients, evidence of recruiting patients, but perhaps unnecessary services being provided. I always say this example, but if you guys aren't on Yelp, people love to complain when they're unhappy. They frequently complain when they are unhappy. They're happy, yeah, maybe you get a good review, but boy, when something happens they don't like, they are really quick to get out there on social media and talk about it. And so if Yelp isn't something that your investigators are using today, you should. So free services, things like offering free strollers, baby showers, if you come and get services there. And as you guys know, these are generally prohibited. You can't do that. And this is another clue that we found, and this was through the integration of third-party data and how we layer that on top of what our models are doing. And what the third-party data showed us, and for those of you for third-party data, we're talking about just data outside of your program, so not your providers, not your beneficiaries, not your claims data. In this case, this was public record property information that showed this pattern where the properties kept changing hands, like quite often. How many of you have used the services of an attorney recently? Is that a great and cheap experience? Who would do these things this often? It does not make sense. And then we started to look at the transferring that was going on, and it was between family members. So there was all kinds of, funny property transfers going on in a way that just made no logical sense until you started realizing which relative was under active investigation at any given point in time, and then the timeline really started to fit together. So in this particular case, I'm just kind of wrap it up before, pass it off to Jacob to talk about his example. But AI and machine learning plus humans is where we found success here, because this initial model output produced a bunch of CAPTCHAs for us to look at, right? A bunch of images. And the ones where we had the strongest evidence, where, our work group team could go through the data, could pull together all the moving pieces and parts and say, these are the outputs that make sense. Here's some adjustments we need to make in the model. Now we can operationalize that model. And what that means is that comes into a system. Now that's where Carrie's talking about, where we can become more efficient and more effective using these tools. You can't take the human out of the middle. You can't go from the model to the dashboard and skip over the human beings. You just can't do it. Or you could, but you're going to spend an awful lot of time chasing your tail. So in this particular case, that's exactly what we did. When we finished our validation and our adjustments to the model, we were able to implement this into the dashboard for that customer. So it's now producing more clusters, just like this one. It's a win. All right, to you.
This is as Gene and I were kind of comparing notes, sharing some war stories to decide, what we wanted to show you guys today. It was so funny how a lot of these things converge on the same topics. So the first one I wanted to show here is a real simple example. You see here, this is all mocked up, by the way. 1 physician, 2 days, 4 members. What do you see? And for those of you who don't know, 99213 is mid-level established patient office E&M. The 90838 is in the add-on psychotherapy service. A few years ago, Medicare changed the policy because of the standalone psych service that was billed by a physician along with E&M was being abused. So they go to this add-on service. So this is something a SME noticed. And once again, going back to pattern recognition, you've got this provider who every member, they bill the E&M, and this is a mid-level in E&M. Maybe they're trying to fly under the radar as far as an upcoding standpoint, but always adding on this psychotherapy add-on service. So this was something working in conjunction with one of my SME colleagues in the past. This was noticed, like, oh, this provider is using these new add-on codes 100% of the time for all their patients, regardless of the diagnosis, what the original cause was. And so this became a study, very productive analysis we did in that environment. So once again, simple data points that you as a human can see. We can teach a machine to see this as well. And maybe if we teach it well enough, the machine will see things we don't see. And one example I use here, and I might have mentioned this before, would you notice if all of these dates were on, say they were all different dates on the screen, but they were all on a Thursday? Or Tuesdays and Thursdays, things like that. So there's patterns that a machine might pick up on, nuance to the data that might be alien to you, or something, a level of detail you might not have seen. So this is the opportunity. The purpose of using AI is to either do more of what you're doing now beyond the resources that you have, or to improve what you're doing now. So that's another example. Would you go to the next slide? This one's actually my favorite example. So Gene went into some convoluted provider networks earlier and mentioned that the authorized official was the same, and that may be the only data point that's linking a cluster of providers. In the past, some colleagues of mine that worked on my team wanted to do some network analysis using the Medicare PACOS data. So this is fairly complex chain of ownership data, mentions authorized officials, phone numbers, things like this, to identify these clusters of providers. Now, take into account we don't want false positives. They excluded hospital networks because they don't want to find, everybody in the Blue Cross network or whatever. So this was the starting point. But there was an instance in a certain state, which I think is mentioned here, Louisiana, where a provider had purposefully set up 4 different businesses using completely different tax IDs, completely different NPIs, and was billing surgical services in one clinic, and then in the other clinic that was in the same city, unbundling a lot of services that would have been caught by the prepayment edit had they enumerated themselves to be known to be the same provider. But in this case, it was purposefully done to avoid that. And the funny story is, skipping down to the last bullet, our case tracking system was set up to look at one provider. And this is as defined by the billing identifiers. So we deliver the referral, kind of go back to doing our thing, and 6 months later comes back and all 4 of these investigations came back as no results. I'm like, well, what happened? Well, it got assigned out to investigators as individual cases. Nobody knew what the other one was doing. So the same way the provider siloed themselves, sometimes our own practices work against us. So we on the data team took this and repackaged it, forced them all back together and said, here, you've got to investigate this as one. Turned out to be a very, very good case, referral to law enforcement in that situation. There's other data points in terms of this network beyond just ownership. Like if you think about shared patients, maybe it's not literally the same provider, but this clustered fraud network that Amanda was talking about, there's patients shared between providers, and you can analyze a network that way. You can also look at the money that's going back and forth. There's a time aspect, so maybe you want to modify the edge calculation between these 2 nodes based upon the time that expired between when provider A saw a patient and provider B saw a patient, where it's stronger the closer they are in time, like on the same day. There's money that flows both ways. Maybe provider A didn't get paid much and provider B got paid more, so there's ways to consider that. In this case, my team that was working on this used the harmonic mean of those two paid amounts for that patient and that provider to inform how those edges were formed. So this was a really good example that was not my idea. It was actually a guy that worked for me, Christopher Sterling. Some of you might know him. If you do, you can hire him. But great example of graph theory and how network analysis can really find things that are purposefully done to obfuscate what's going on in the billing system. Another example, and this was the brainchild of another colleague of mine, John Short, looking at, so who knows what NLP is? Yeah, I think it's a pretty well-known term. So, NLP using things like semantic analysis and social media, how we're, looking at this unstructured data, there is a corpus of text that NLP is applied to analyze the words and what the meanings are and the underlying context. Well, if you think about, beyond EMR, EMR is a trove of unstructured data that increasingly we are getting access to, but think about just the claims data. A CPT code is a character string. It doesn't necessarily mean anything in itself other than how it's defined in the CPT manual, but then there's another service that's provided on the same day, and then the next service on the next day or the next time the person sees the provider. And so if you string these things out into a sequence, you essentially have a story about what's happening with this patient, their healthcare journey, if you will. And so, everybody spent a lot of time on episode groupers and stuff. A lot of those are rule-based at this time. This is a way deriving from the story that happens in the data with a member's diagnoses. For instance, it could be refined down to identifying certain types of cancers. This is, we use these rule-based methods. Like, we want to make sure people have this condition that would necessitate this service the provider's billing. So let's go and look and see if they have this diagnosis code in the past. Well, what if that provider was the one who assigned the diagnosis to the person to get paid? What if there was a test in the past and that diagnosis was used on the member for the test, but then it came up negative? So the rule-based aspect has a lot of inherent flaws. If we look at the data, the story that's available to us at the member level, we can differentiate these things from a data-driven standpoint. And likewise, from a provider standpoint, the specialties that exist in your provider enrollment system and whatever provider data you have may or may not truly reflect how that provider's practicing. I think we've all struggled with that by using these data-driven techniques to read what kinds of services the provider tends to provide, the basket of services to the same patient, and over time we can start to distinguish from an empirical standpoint what kind of provider that is, and maybe that is to establish what the norm is, to see who falls outside that. Maybe that is to see whether they actually have the credentials to be providing the services they're claiming to provide. So NLP also has applications when it comes to healthcare fraud, waste, and abuse.
We're going to skip a couple examples here. They'll be available in the conference materials if you want to go through and see those, because I want to make sure we have enough time to talk a little bit about some take-home techniques, and then that we have time for questions as well. So if you've been thinking of questions while we're talking, get those ready because we're just about there. So, these guys are obviously brilliant at what they do, and I'm constantly learning what I would call layman's ways to describe some of these techniques. So whenever they can break it down to me in something I'm familiar with, like the last case example is, Jacob was walking us through it as we were, kind of preparing for today. The Facebook ad thing just struck me. You always wonder, why am I seeing this ad? Why is this in my feed? Or, why does LinkedIn think I might be interested in purchasing this or that? And so when you take something like that, most of us are fairly familiar with, and you go, yeah, I get that, I understand it. And then, break it down in that way, it makes a lot more sense, at least for, us cops in the room. So the partnership of humans and machines was the theme of the session today. Hopefully we wove that in there, throughout. And again, you can't skip the step, right? So you have capabilities like Carrie described that we didn't have in the 50s. We were inhibited by what technology could do to help us solve this problem. And now we're in kind of an opposite place where I think people are very quick to want to use the technologies and skip the step, and you can't skip the step in between. That thing that happens in the middle is where the magic is. And I think when we do that and we use the humans to develop a training set, Jean talked a bit about that training data set. What is that? That's what we know is fraud from our experience and our interaction and our work in this profession. Those are the knowns, right? We can use the humans to design the appropriate way to prepare the data. Lots of things that, a technical or a database person might see in the data, we're going to go, oh, yeah, let me explain how Medicaid works. Okay, so this is actually okay. This happens. Some of our younger data scientists sometimes will come and say, hey, I think I found this pattern. This guy's providing tons of services. It's impossible. Look at this. And I'll say, it's home health. They didn't actually do all that. So, you have to explain, sort of the reality of how Medicaid is facilitated. And I think that's a really important component of humans and the partnership here. Identify true and false positives and give feedback to the models. And this is so important. We use a term a lot, outcomes data. Sometimes we have outcome up front and we know what we want, and sometimes we gotta run the model and somebody's gotta knock and talk. You gotta get out there, you gotta see what's in the field, you gotta pull some records, and then there's that learning that has to be infused back into the model. Only the humans can provide that. And then iteratively modify the algorithm and the data preparation. That's the last and final pieces. First time you make a recipe, it's never as good as the 20th time you make it, right? So you're always perfecting a little more salt this time or whatnot. And so you have to build that continuous improvement process and plan for it. Don't be surprised by it. It isn't plug and play. You don't set it and forget it. It constantly needs adjustment. And then what happens to us in Medicaid? Policy changes, the providers pay attention to that. They slightly tweak their techniques. You have to adjust the model to account for that. So it's constant process. Jean and Carrie, I think, had some other suggestions too that, sort of things to take home and think about in terms of best practices.
Yes. Well, first of all, I think you heard earlier, please be aware of fool's gold, because when somebody brings up something to you and they have a performance metric, make sure you have them interpret that. Don't take a number and assume it's going to work if you apply it to your data. You need to understand. And most machine learning algorithms are explainable. Neural nets are an example, or the exception. You can't explain neural nets, but machine learning out decision trees, logistic regression, all of these algorithms are explainable. You can say, well, these are the variables that made me decide this particular provider was fraudulent, and this is how I combined them. So have them interpret the algorithm is very important. Don't just take the performance metric on face value. And as I say, consider a hybrid approach. The approach that we use, I think, is a good way of combining the strengths of supervised and unsupervised learning at the same time. Data preparation, again, it's so important to recast your claims in a form that relates to what you're trying to do. Don't just throw the data at the algorithm. It's not going to work that way. And then also make sure that if you can, for your data scientists, give them something that they can use themselves independently. Minimize the dependence on the IT department. You need for them to be as independent as possible, and especially in the big data world, machine learning algorithms often require custom developments. The package applications for machine learning really have problems when you try to put big data on it. And healthcare data is big data. We're talking about hundreds of millions of claims, even billions. So give them a tool that they can, if possible, develop their own custom algorithms to implement machine learning algorithms. And I think you have one more, Carrie?
Sure. So 2 things. I just want to take it back one step. If you're trying to get started with AI, you're trying to figure out what is this beast that is artificial intelligence, I would encourage you to go after what I built a workshop for state and local government the last fiscal called Approachable AI. And it just means exactly that. It's meant to completely lower the ramp for entry so that you can figure out how to start to understand it and leverage it. This is a sway. Just very quickly, is anybody in here, have any of you used the cognitive services within Azure? Okay, that's good. This will be right at the right level then, because that's what we were betting on. So if you click on this link, with apologies for the funny link, that's the only way Sway will let me share it. I believe Amanda can get you this deck. If you click this through, I built this, okay? My contact information should be in it. And it's a step-by-step, how would you go about using the package services of Azure? They're very, very, very inexpensive. You can sign up for free, and you can get in there and start to mess with it and try to answer your own questions. Because I don't know about any of you, but when I'm a data and business intelligence architect by trade and training, and when I got into AI, I was like, what is this thing? I'm not a data scientist. How am I going to learn this? Well, this is how I started to learn it. I got in there and I dug around, and I figured out how to leverage it with a low, no-code approach. Once I understood it, I would go to the second place, which picks right up on what Jean was saying. There's a tool called Databricks. If you haven't heard of Databricks, it's designed for exactly what you guys are here talking about this week. It's meant to take massive amounts of data, facilitate collaboration between data analysts, data architects, and data scientists, and to very quickly crunch through those numbers with custom algorithms, and you can hook into all different languages, so sort of meet the people where they're at. And then you can run that in the cloud. So talk about being able to spin things up, spin things down. You're not trying to do a huge CapEx to get started. Lots and lots of opportunity. But if you want to try something super simple, try this Sway. The only catch being that you will have to spin up Azure.
And this Sway link will be in the materials that NAMPI makes available, but if you'd like it sooner or you want it directly emailed to you, you can stop by our booth, leave us a business card, and then we will be sending the whole presentation to you after the conference if you'd like. So make it super easy. And I actually clicked through this and didn't need to Google a lot of words. So it truly is approachable. If you have some high-speed analysts in your team, maybe you're not fortunate enough to have data scientists or to have an opportunity to bring a vendor in, probably your high-speed analysts could look at this because, as Carrie mentioned, it's low-code approach. That's what I like. Okay, so we do have a few minutes for questions, so I hope you've prepared some. If not, I always have questions for these guys.
Hi, thank you for the presentation. I just have a question about, for the case example, the provider profile. I'm just interested if you could expand more on that. Is that based off of aggregates when it comes to utilization and diagnoses, or are you building off of patterns?
Yeah, there are several ways to prepare the data. The one that I use, I find that the most useful is to calculate the paid amounts as a percentage of the total for each provider. So, so you get, and do that for diagnosis codes and for procedure codes separately. And that produces a nice profile. Now, sometimes, especially in Medicaid has a lot of special procedure codes for each state. And often these are kind of ubiquitous. I mean, they mean a lot of things. And if you cluster without just doing what I just said, you're going to wind up with a lot of unrelated providers in the same cluster. So when you have those codes, I knock them down by a percent. And so that for example, if there are providers that file mostly the same procedure code, but they're doing different things, you look at the diagnosis codes instead. So you can force the model to do that by dropping down the percentage on those procedure codes, and then up it again before you actually report it out. So there's several ways of doing it, but that's the basics. Yeah.
Thank you.
Wow. Oh, yes. Okay. Some of you guys who know me personally were about to be called on.
I guess I just had a basic question. When you were going through your example and you were saying, and then we saw this, and then we saw that, then we saw this. Okay. What is the machine learning giving you exception notices? What are you doing to see that?
That's a really good question. Yeah, so hopefully everyone heard the question was about the case study example where we talked about how we were diving into a particular output of that cluster analysis. So nothing goes into our system that doesn't go through this process. There is no model output that is, raw and initial that we then just go, here you go, because we try to be that step in between. And so part of that process is we do have a work group that's put together with lots of different types of disciplines and approaches. And when this initial output was run for this client's data set, the very first thing that we did was that validation process, where we go through, this one kind of walks like a duck and it talks like a duck, but let's dig in and see. And so using other analytic outputs from the system, using integration of outside data sources, we're able to go through and validate, but also surface tuning or adjustment to the model that needs to occur, things that we need to account for, whether they're state-specific Medicaid policy or just Medicaid policy in general that can be, explain away certain examples so that we can control to the best of our ability for false positives. So that was one of the outputs from that initial model, the initial run of the model that actually turned out to be a pretty good fraud case that's currently being investigated. But then we used that information, that validation process to improve the model before it was delivered in production. Does that help? Sure. I don't know if you want to add anything, Gene, in terms of the clustering. That might answer his question.
I think maybe look at the example. It's the easiest way to go.
So are you talking specifically about this data? That's peer. Can you talk about paired providers? Did you hear his question?
I'm not totally understanding it.
Yeah, he's asking about the similarity,
Yeah.
the heavy similarity between the providers. And was that something that a human had to scan the data to find, or did the model actually surface that?
Well, what we do is we look for the paired providers, for example. It's a combination, again, of humans and machines. But the basics is we calculate a similarity index that starts out looking at the number of shared beneficiaries and looking at the total beneficiaries for each provider. And there's a formula you can use when you have disparate sizes to come up with the similarity index that works. Then we also look at, for example, you'll have a lot of providers at the same address that might have similarities which are very understandable. So actually in our paired providers, we provide a lot of address matching and name matching, but using fuzzy matching and using something called K-tuples matching, which actually is something that's derived from the bioinformatics for DNA and protein strings. And we provide that for the user so that they can then go in and say, okay, I don't want anything where the name is similar in any way or the address is similar in any way. And as well, we calculate, of course, the miles between the zip codes for the two paired providers. And there also has something called a billing and paid similarity, where we look at, well, what if one provider is getting all the money and one of them is not? So you look at the similarity in the payments made for each beneficiary to the two providers. And so we provide a number of ways that the user can get in and start playing around with the data to determine, well, just based on patient similarity, that's a start. But maybe I want to go further and filter that down to something that's more meaningful in my particular investigation. Does that help?
I think we had one in the back over here.
Hey, we just had a comment, Becky and I, and we were going to speak on this because we are considered SMEs in our particular area. So one way the SMEs can also help you, and I didn't see this going through, is on that front end process when you're preparing the data. Because often, if they know about the clinical, they've worked with it, they also understand the billing and how the claims data should look. So they can help you get that cleaned up on the front end, as well as help you on the model.
And I can attest to both of them being fine SMEs at data setup. So Bev's right.
Absolutely, we would agree. We're working on a new model now that actually specifically looks at mental health services within a specialized program for a particular client. And Jean started diving into the data, and the very first conversation we had, there was a nurse on the phone, a physician, a former law enforcement, couple analysts. I mean, we threw everybody at this, and we're like, okay, let me explain this to you. This is how the program works. Here's the kind of fraud we see in it. And it really, I mean, Jean, you can speak to how much I think that helped you in order to stage the data properly to run these models on it.
Oh, absolutely. You need that input in order to know what to look for. Because you've got to have you can't just go in there and say, I'm going to look at aberrances. You've got to have the input from the people that know about the data to know kind of where to dive in and what to look for. It's really, really important. Yeah.
And sometimes we look for risk backwards. And what I mean by that is you can read a policy handbook, and I try to read it like the bad guy, right? So where's all the places that I can sneak in, or what are the ways that I can take advantage of how this particular program is administered, what edits might be in place, and look at it, and kind of reverse engineer how might that look in the data. And oftentimes you hit pay dirt that way.
Yeah, and in Medicaid especially, Medicaid is very different from Medicare in that Medicaid has a lot of state-specific programs. And state-specific programs, and they're often very good programs, but they open up vulnerabilities, and because they're limited to that state, sometimes those vulnerabilities aren't caught as quickly as you'd like. So it's very important to find the people that know about those and try to make sure that your special programs aren't being taken advantage of.
Other questions?
I have one question for Jean.
Oh.
Were you the brilliant PhD candidate in Florida in the 90s?
Now you have to ask me. Yeah, I was the guy. He wasn't so brilliant. He wasn't so brilliant after all. He had the tools, right place, the right time.
Well, thank you so much for participating in the session. I didn't catch anybody sleeping. Go team! It's the last session of the day, so I know you guys have things to go. We have a reception coming up. But if you do have questions and you didn't want to ask them in the broader group, there's a lot of ways you can do that. You can stop by our booth, and we're happy to answer the questions there, provide you contact information. These guys are all very approachable. Thank you.
Thank you, Gene.
Yeah, really enjoyed it. It was fun. Yeah.
I